Traditional software engineering relies on rigid deterministic logic. If A, then B. But machine learning models for autonomous vehicles operate on probabilistic inference, calculating the likelihood of a safe path through chaotic environments. In machine learning, ground truth refers to the specific collection of human annotated labels used as a training baseline. These labels represent a consensus at a single point in time, subject to revision as domain knowledge and sensor data evolve. Creating this data requires human workers to manually draw boundaries around objects inside complex 3D point clouds and high-resolution images. Staring at thousands of frames induces severe cognitive load and fatigue, making human error inevitable. When fatigued labelers make slightly different subjective choices on where an object begins and ends, they inject inconsistencies into the dataset. The AI model absorbs these contradictions, amplifying its own predictive uncertainty. The margins for error are razor-thin. Research shows that a 10% drop in labeling accuracy can degrade the model's overall performance by 2 to 5%. On the road, that degradation translates directly to a vehicle's autonomous emergency braking system failing to recognize a pedestrian in time. To prevent these failures, the autonomous driving industry is adopting strict standards like ISO PAS 8800. This standard mandates that training datasets can no longer be treated as mere raw material. They must be regulated and managed as safety-critical engineering artifacts. Safe autonomous operation depends on a mathematical and organizational structure that systematically removes human subjectivity from the data pipeline. Consider the development of an autonomous emergency braking system. The AI model must be trained to reliably detect pedestrians during heavy rain, a scenario where visibility drops and sensor data becomes noisy. During data collection, the cameras capture a specific anomaly, a pedestrian crossing the street while holding a large, completely transparent umbrella. The human annotators must decide how to label this object. Labeler A takes a modal approach. Because the umbrella is clear, they ignore the material and draw a tight bounding box strictly around the visible human torso. This diagram illustrates the conflict. Labeler B takes an amodal approach, drawing a massive bounding box encompassing the umbrella's furthest edge, the true collision boundary. This size discrepancy represents a critical consistency defect, creating conflicting pedestrian definitions. Because the box dimensions differ, the model's center point calculation shifts violently. The AI relies on that center point for distance estimation, which fluctuates every frame. When labeling interfaces are complex and specific guidelines for edge cases are missing, workers unconsciously fall back on their own surface-level visual interpretations. This embeds systemic human bias directly into the training data. The vehicle's emergency braking system is fed this conflicting data on physical boundaries. Unable to determine the exact distance to the obstacle, the system delays its braking response until its certainty threshold is finally met. Millimeter-perfect LiDAR and ultra-high-definition cameras are rendered useless if the human-defined parameters governing those sensors contain systematic logical contradictions. Solving this requires abandoning ad hoc data collection. The industry must apply rigid systems engineering principles directly to the data pipeline itself. This diagram illustrates the Dataset V-Model, adapting the software engineering lifecycle for machine learning. On the left, data requirements are derived from system safety goals, ensuring label traceability. On the right, continuous verification loops prove the dataset has sufficient volume and representativeness for real-world driving. Before a single image is labeled, this framework requires explicitly defined quantitative quality criteria. Organizations must set strict parameters, such as a maximum 2-pixel error limit for bounding box precision. Because annotators will inevitably encounter unpredictable anomalies like the transparent umbrella, the system relies on an active incident reporting pipeline to capture these edge cases the moment they are discovered. Safety managers analyze these reports to instantly update the labeling policy guideline. They create explicit rules and decision trees dictating exactly how to handle occluded or anomalous objects. Through a rapid feedback loop, this updated rule is distributed back to all annotators simultaneously. The subjective guesswork is removed and replaced with a uniform standard. Implementing the Dataset V-Model transforms static data labeling into a dynamic, traceable safety argument. It provides the documented proof that the AI is operating strictly within acceptable risk parameters. Even with strict guidelines, human error persists, and conducting a 100% manual inspection of millions of high-resolution image frames is economically and temporally impossible. To filter out human error in high-complexity data, engineering teams implement multi-annotator cross-validation and consensus models. This diagram shows how consensus is measured geometrically, using intersection over union, or IOU. Multiple independent workers label the exact same object. For autonomous systems, their bounding boxes must achieve an IOU overlap threshold of 0.75 to 0.90 to be automatically accepted as valid ground truth. If the annotator's boxes fail to meet that strict IOU threshold, an escalation protocol triggers. The system either relies on a majority vote among a larger pool of workers, or it routes the conflicting image to a highly skilled expert adjudicator for final approval. Once individual images are verified, the process scales to population-level verification across the massive dataset using strategic sample selection. Relying on simple random sampling is deeply flawed. It is highly ineffective at catching critical errors hidden inside rare edge cases or complex low-visibility scenarios. Instead, engineers use model-based uncertainty quantification. By analyzing the model's softmax outputs or entropy levels, they automatically hunt down specific frames where the AI clearly struggles to understand the labeled data. This script filters the entire dataset, isolating only the top 1% of highly uncertain labels. Human auditors then perform targeted, manual compliance rate inspections on this specific subset. Merging tight IOU consensus thresholds with strategic statistical sampling provides the scientifically valid method necessary to isolate and eliminate human error at an industrial scale. Even with perfect mathematical consensus, another vulnerability exists: the engineering instinct to capture absolute, flawless ground truth by physically altering the real-world environment during collection. To extract highly precise 3D skeletal data, engineers frequently attach bright motion capture markers directly onto the joints of pedestrians before recording them. This introduces a catastrophic flaw known as representational bias. The engineers have injected artificial physical interference into the dataset. This heat map shows how the neural network interprets the image. The model learns to identify the highly visible geometric pattern of the markers. It completely ignores the underlying human anatomy. The consequence is immediate and dangerous. When the trained AI encounters normal, unmarked pedestrians in real-world operations, its recognition capabilities collapse entirely. Data collection methodologies must preserve the natural representation of the world. The process of measuring the environment cannot alter the environment itself. To achieve this, engineers deploy markerless MoCap algorithms that track movement visually, utilize independent sensor fusion with precise RTK GPS coordinates, or generate completely synthetic data via virtual simulators. Injecting artificial physical markers to gain measurement precision ultimately destroys the natural data integrity required for an autonomous AI to accurately perceive and survive in the real world. The labeling process establishes the core logic of the vehicle's perception system, requiring oversight as rigorous as the software code itself. Through every bounding box, human annotators define the moral judgment criteria and physical safety boundaries that 2-ton machines will obey. Accumulating petabytes of raw sensor data cannot compensate for a lack of structural integrity. Without rigid ISO PAS 8800 compliant organizational defense structures, that data is just noise. True safety relies on mathematically verifying every single human label through strict IOU consensus, while rigorously guarding the collection process against any physical measurement interference. Only this deeply engineered, relentlessly verified ground truth will successfully constrain AI unpredictability, ensuring that autonomous systems actually protect human life on the road.